Well, today we're going to talk about how we can add velocities together. I had you read an example in your book that involved airplanes and wind. So we'll go over that example first, and then I'm going to show you another one as well. So just ignore this stuff on the top of the board for the moment. This is supposed to be an airplane, and this is the point in the class where my students tend to make a whole lot of fun of me because I'm really not a very good artist. So take my word for it, that's an airplane, okay? The airplane is moving at 720 kilometers per hour to the west. Now, I understand that probably a lot of you are overseas. You've probably spent a lot of time on airplanes, and so you understand the effects of wind. And so you know that a lot of times when you're traveling one direction, the wind helps you and gets you there faster. And when you're traveling the other direction, you're traveling into the wind and the wind slows you down. Well, for the purposes of this class, we're either going to be going straight into a headwind, or we're going to have a wind that's going to directly be coming from behind, just to make it simple. When you get into physics, if you take physics later on in high school, we'll deal with crosswinds and winds that are coming at an angle and what kind of effect that has. But for the purpose of this course, we're not going to do anything quite so complicated. Okay, so if your airplane is going at 720 kilometers per hour to the west, and the wind is also blowing, and it's blowing at 80 kilometers per hour to the west, is that a good thing or is that a bad thing? Well, again, you probably realize that if the wind is blowing the same direction as you do, then that's going to help you out. And so the ultimate effect here then is going to be 720 plus 80, which is going to be 800 kilometers per hour to the west. Okay, so it's going to actually speed the airplane up in this particular case. Okay, so I can just add those two vectors together because they are going the same direction, and so it's going to give me a higher speed. Now, what happens if the wind is going the other direction? Let's say that the wind is going 80 kilometers per hour, but let's say that it's blowing straight to the east this time. What does that do? Well, it's going to slow you down, obviously. And so in that case, since this is going to slow me down, I'm going to have to take 720 minus 80, which is going to give me 640 kilometers per hour. This one's bigger. The airplane is still going to continue going forward, so the direction is still going to be west. But the magnitude of its velocity is not going to be as high because now I had to subtract those two numbers, okay? So you can see the effect there on airplanes and wind. You can feel it if you're riding your bicycle, either into the wind, or if you've got a tailwind, you can feel it when you're running. My daughter and I do a lot of running together, and we don't enjoy running into the wind because it slows us down and messes our times up. So. But running into the wind, we're good with that. So the wind is definitely going to have an effect on things that are moving. Sometimes, though, what you want to do is you want to compare two objects that are moving in relation to each other. So again, if you have the sample problems for the videos, there are a couple for video number 3, and those are the two that we're going to be looking at next. So the first problem says this. Two cars are traveling down a road. The first car is traveling north at 55 miles per hour, and the second is a few hundred yards behind, traveling north at 45 miles per hour. What is their relative velocity? Now, when I'm talking about relative velocity, what I really mean is what the velocity of one moving object looks like in terms of another moving object. You've probably experienced this if you've ridden on the interstate, and maybe you've got a big semi who's passing you, so you're going along at this rate, and the semi is coming up and he's passing. You're both still moving forward, but from your vantage point in the car, the truck is moving ahead of you, but he doesn't appear to be moving very fast if you focus only on the two of you. He's moving just at kind of a snail's pace as he's kind of crawling along beside you and eventually passing you. The same type of thing is really happening here. And so what I really want to encourage you to do is when you're working problems like this, you need to draw a picture. You don't have to be a great artist. It doesn't matter what your cars look like. I'm not expecting you to take a whole lot of time and draw sports cars and Lamborghinis and fancy things like that. Just a car. So, for example, here's a car. Okay, see? Nothing fancy. It's just a car. I guess it would probably help if it had a window in it, but regardless, I have some sort of a car there. So the first car is traveling north. So we'll say that this way is north. It's traveling north at 55 miles per hour, okay? The second car is a few hundred yards behind. So we have a second car back here, and it is also traveling north, and it is going at 45 miles per hour. And we want to know what the relative velocity is. So if you look at this, what's happening with these two cars? Is this one going to catch up to this one, or is this one pulling away from this one? Okay, well obviously because the car in the front is moving faster, it's going to gradually be pulling away from the car behind it. How quickly is it pulling away? Well, because they're both going the same direction, I need to subtract these two numbers to see what the difference looks like between them. So here I'm going to have 55 miles per hour minus 45 miles per hour, which will give me 10 miles per hour. But remember, velocity always has to have a direction on it. So what's the direction? Well, in relation of the two cars to each other, they're actually getting further apart because this one's pulling ahead. So the direction here is going to be 10 miles per hour away from each other. Okay? Now, this is not the same thing as we were doing with the wind, because the wind is directly affecting the motion of the airplane. This car is not affecting the motion of this car, so that's why this problem looks completely different than what we did before. Hopefully it's intuitive to you that, you know, if a plane is going with the wind, it's going to push it, so you're going to add it, and if a plane is going into the wind, it's slowing it down, so you're going to subtract. Okay, here though, the rules are a little bit different, and so keep in mind here, maybe you've just been passed, maybe you're in this car and you've been passed by this one. So this one's moving ahead and it doesn't certainly look like it's going this fast. It looks like it's going slower. So if your objects are moving in the same direction, their relative velocity is the difference between their individual velocities. So I'm going to subtract to find out what they are relative to each other. So they're pulling away from each other at 10 miles per hour. Now let's look at another example, because the second example here is a little bit different. It says two cars are traveling down a road. The first car is traveling north at 55 miles per hour, and the second is a few yards behind, traveling south at 45 miles per hour. What is their relative velocity? Okay, so again, we're going to draw a picture here. And our first car is traveling north at 55 miles per hour. Okay? The second car is a few hundred yards behind. So again, the picture looks really similar, but this time he's going at 45 miles per hour, but this time he's going south. So he's going this way. Okay, so they're going opposite directions. So now what's their relative velocity? Well, if I look at this, when you are in a car and you see another car coming towards you, it looks like they're coming a whole lot faster than they would be if you were standing on the ground and watching them. Okay, so it's not like I'm standing still and I'm watching this car go by at 45. I'm going this way at 55, while this car is going this way at 45. And so the effect here is that if objects are going to move in opposite directions, their relative velocity is the sum of their individual velocities. So here, I'm going to take the 55 miles per hour and I'm going to add to it the 45 miles per hour. And this time I'm going to come up with 100 miles per hour, and they're still moving away from each other because of where they started, away from each other. Okay, now, had I started with this car up here, and they're coming toward, then I would say their relative velocities are toward each other. That's why it's so important to read your problem carefully and draw a picture so you can see exactly where everything's located. So I want to make sure you draw that picture so you can see it well. Okay. When you look at this, you can see why head-on collisions in cars can be so horrible and why they often have fatalities. If you run into the back of somebody, then there's still damage and there's still people hurt, but if you're both going the same direction, the relative velocity is a lot smaller than if you are going opposite directions and you're heading straight at each other. So if I had this car up here, this one's going at 45 this way and 55 this way, it's like you're colliding with something that's stationary at 100 miles an hour. That's going to cause a lot of damage. And again, that's why head-on collisions cause so many fatalities, is because they're going at opposite directions, and so those effects are additive. And so that's why you want to make sure that when you're driving, you stay on your side of the road and the other guy stays on his. Okay, so you will again have several examples of problems where you are calculating relative velocity.